So in the previous lecture, Bismillah ar-Rahman ar-Rahim first. Yeah, Bismillah ar-Rahman ar-Rahim. In the previous lecture, we started the analysis procedure of sequential or clocked sequential circuits. Okay. And we said that it goes over 4 steps. Okay. However, I have added one small step. Okay, which is basically it is a little bit of details, and it adds more convenience rather than it's a required step. Okay, but you must know it and you must understand the concept behind 2D state table anyway. Okay, so we said that the first step is to obtain the equations, the Boolean equations, for every D input of the flip-flops. And this is basically the next state equations. Okay. Step number 2 is to obtain the output equations. If you have more than one output, then you obtain them all. Okay. Step number 3 is to fill in the 1D, one-dimensional state table. Okay. This is the state table that we have seen in the last lecture, the one that I recorded offline. It's called one-dimensional state table, or even more formally, one-dimensional state transition table. Okay, because it shows you the transition from state to another. Okay, how the state machine performs the transition from one state to the other. Okay, depending on input and the present state. Okay, so the next step is to fill in or obtain the two-dimensional state table. From this, you can see that the two-dimensional state table is another form of the state table. It's just twisted in a way to make it two-dimensional. Okay. So just to give you an example of what I mean, a truth table is a one-dimensional structure. Truth table is a one-dimensional structure, whereas a K-map is a two-dimensional structure. Okay, you can see that in the K-map, if you remember, we have variables going horizontally and variables going vertically. Okay, whereas in the truth table, all the variables goes horizontally. Okay, I mean vertically. I'm sorry. So step number 3.5. Okay, I squeezed it in between 3 and 4. Okay, it's to fill in a form of the state table, which is called a two-dimensional state table. Okay, and then we obtain the state diagram either from the 1D state table or more easily from the 2D state table. Let's see an example of what I mean by two-dimensional state table. Okay, so I'm going to convert now. This, we have done this in the previous lecture. Okay, this example we have done it completely in the previous lecture. Okay, now I'm going to take the output of step 3. Okay, and then produce, which is basically the one-dimensional state table here, and produce the two-dimensional state table out of this. Okay, now this is the 1D state table shown here on the left-hand side of the page. On the right-hand side of the page, I'm going to draw or obtain or write the two-dimensional state table. Okay, so for the state, the present state, there is no difference. Present state, which is basically denoted by Q. Okay, there is no difference. For the input, now the input is not going to show as a column. Now it's going to show on the horizontal axis. Now the input is going to show on the horizontal axis. So the input can be a 0, it can be a 1, and the present state as well, it can be a 0 and it can be a 1, right? So for the present state, we only have two values, either a 0 or a 1, right? Now for the next state, okay, let's put dots here. The next state, okay, depends on whether X is 0, which is the input, or X is 1. And in each case, we have a D, okay, which is the next state, okay? This is D for X equals 0, and this is D for X equal 1. Do you see the two-dimensionality now? Okay, so this is what we mean by the two-dimensional structure. All right, now for the output, also I have the output when X equals 0 or the output when X equals 1. And the output is denoted by literal Y. All right, now this is how you populate the values in the 2D state table. It's just a transformation from here to here, okay? So I have the present state being a 0 and the input being a 0. So 0, 0, 0, 0. What is my next state? It's going to be a 0, right? And my output will be a 0. So this D is going to be a 0 and this Y is going to be a 0. You see that? You see that? So this is going to be a 0 and this is going to be a 0. What about when they are 1? When X is 1. When X is 1, okay, my D is going to be a 1 and my Y is going to be a 1. So it's here, 1 and 1. Okay, do you see that? Anyone not following here or having confusion or being confused or something like that? Please ask. If you're not following, then this is the time to ask, okay? Do you get where we get these numbers from? I need a confirmation from you that you understand where these are coming from, guys. Anyone? Anyone is following? Anyone is not following? Anyone is challenged by this or find it difficult? I guess all of you are asleep. Just a hunch here, okay? It's very the participation level here today is very low. So please, guys, wake up and participate, okay? I'm asking you, is this clear now? Is the two-dimensional state table, is the construction of the two-dimensional state table clear to you?
Yes.
What is, okay, you said yes. Who's that?
Me.
Hassan.
Hassan.
Okay, Hassan, I want you to populate the second row of the table. So when Q is 1 and X is 0, what is my D?
Q is 1.
What's that?
Say again.
I want this one here. I want this slot here.
Okay.
So Q is 1 and X is 0.
0, 0.
It's just
for the output.
So you're giving me the D and what?
The Y.
Y. So it's what? 0,
0.
0, 0. So you're reading it from here, right?
Yes.
What is this? 1 and 1. And I asked you, I said 1 and 0, not 1 and 1.
Oh, okay.
It must be what?
1, 1.
1 and 1. And the case for the, now you get it, right? You get it, Hassan, now?
Yes.
Yes, so this is 0, 0. Okay? I hope that all of you got it. Okay? Now, we also talked about Mealy and Moore machines last time. Okay? And we said that Mealy machine, pay attention here because I'm going to ask you what kind of machine is this. Okay? So pay attention. Pay attention to my explanation of Mealy and Moore machines. Okay, so the Mealy machine, in the Mealy machine, we look at the output, and if the output depends on both the input and the present state, then this is a Mealy machine. And graphically speaking, this is the output here. This is the output, okay, and this is a combinational logic block for the output. If the output depends on both the present state and depends on the input as well, the external input, then this is a Mealy machine. Okay. However, if the output only depends on the present state, then this is a Moore machine. Okay. Now look at the two-dimensional state table, okay, and tell me whether this is a Moore or a Mealy machine. Come on, guys. Come on.
More, Doctor.
What's that? Faisal?
More machine.
Raise your voice. I can't hear you.
Is it more?
Moore. You're saying it's Moore machine, right?
Yes.
Why?
Because we only are taking from PS.
Okay, so Moore machine here, the output depends on the present state, right? Only. But from the 2D state table, the output here, you can see that the output, when x is 0, for the same state, output is different than when x is 1. Do you see that? Faisal.
Yes, yes.
So it's not a Moore circuit. It's not. So it must be a what? Mealy machine. Okay. I'm going to do the same now for a different circuit. I'm going to derive the 2D state table for a different, the last example that we did, okay, last time, and then decide whether it's a Mealy or a Moore machine, okay? So this is the example that we did last time, all right? So this is the 1D state table. You can see that I copied it here, okay? And this is the 2D state table. So we have the present state, which is A and B, okay? And it has 4 states, as you can see here. 2 bits, so 4 states, right? And the input, which is D here, denoted by D, input is D, can be a 0 and can be a 1. And the next state for the 0, okay, we have DA and DB. And for the 1, we have DA and DB. So we have 4 columns here, right? And the output, which is called Y here, for Y when D is 0 and Y when D is 1, okay? I'm going now to fill it, and I'm going to ask Hassan, let's see whether he understands or not, okay? So Hassan, tell me, what do I put here? For DA, just DA, okay? DA when this is the present state and this is the input.
0.
0, excellent, okay? And what about Faisal Al-Ali? Faisal,
Yes.
DB.
Also 0.
0, okay? And then the next one, you just read it like this. 0, 0, 1, 0. 0, 1.
1, 0.
0, 1, 1, 1. 0, 0, 1, 0. You see that? So it's like this. So this is going to be 1, 0. And then the next 4-bit, which is 0, 1. And then 1, 1. All right? And then 0, 1, 1, 1 again. And then 0, 0, 1, 0. All right? What about the output now? Output is, it's going to alternate between D equals 0 and D equal 1. See? D equals 0 1 0 1 0 1 until the end. So it's 0 0. So the filling is this way. Okay, so it's 0 0 1 1 0 0 1 1. So look at this circuit from the 2D state table and tell me if the circuit is a Moore circuit or a Mealy circuit.
Some more.
Moore, why?
Because it's depend on present state.
Only, right? Only the present state, because for all the present state combination, okay, the output is constant, okay, and it does not depend on the, I mean, for any pick any state, any present state, the output will be constant and does not depend on the input. But for if you just discover only at least one of them is different, then it's a Mealy, okay? You see here it's 0 0, regardless of the input. Okay, 0, and then 1 1, 0 0 1 1. Okay, so this is a Moore circuit. Moore machine. All right. Okay. So this is what I wanted to show you, which is the 2D state table now. The next thing to do is to discuss the design of clocked sequential circuits. Okay. Now we concluded the analysis of sequential circuits. If you haven't watched the video that I recorded offline last time, please make sure that you watch it. Make sure that you watch it. And if you have questions, please ask during the office. Ask for office hours, and then I can clarify that to you. Okay. All right. Now we switch to the design. Okay, the design of clock sequential circuits, and basically the design is 5 steps. And if you can think of it as the reverse procedure of the analysis procedure. Okay, we start with a verbal description of the problem, and usually this is given to you as part of a problem. Okay, and then so you start usually with step 2. Okay, the second step is to derive what we call a state diagram. Okay, state diagram, we have seen it before. Okay, but for the design procedure now, the state diagram is going to be a symbolic state diagram, because we don't know the number of states, okay, and we don't know what each state represents. So we just assign, we just symbolically generate states as much as we need, and then eventually we will assign these states using state assignment. We'll assign them binary codes. Okay, this is step number 3. So binary state assignment is step number 3. And then step number 4, we can easily derive a 2D state table from the state diagram. Okay, from the assigned state diagram. All right, we can easily derive a 2D state table, and then we can use K-map to find the minimum next state equations and output equations. And by reaching this, you are done with respect to the design procedure. Okay, all you have to do now is to sketch the circuit. Okay, sketch the circuit, because you already have the equations for the circuit, and you only need to sketch the circuit. Everything is clarified using examples. So in this example here, we would like to design a clocked sequential circuit, okay, that detects the sequence 101 with allowing overlaps. Okay, so imagine a box like this, which is a clocked sequential circuit. Okay, this box is a clocked sequential circuit. Let me just this is a clocked sequential circuit, and it has, since it's a clocked, it has an input clock here, and it has a serial input X. This X is 1 bit, so X is going to be is going to contain a value every clock cycle. Okay, and after a few clock cycles, if we detect the sequence 101 on X, okay, then my output, which is here, Y, let's call it Y, okay, my output Y, all right, will be 1 for a complete clock cycle, okay, and then it will go down, it will go down after this cycle, okay, and it will be 1 every time the sequence is detected, okay. So let me give you an example. Now, we haven't started the problem solution yet. All of this is the verbal description, is part of the verbal description, okay? We're still at the verbal description of the problem. So this is, let me just raise the one below here. I need to do it again, okay? Yeah, right in front of you. So you have to see it developed little by little in order to get it, okay? So here is the example. So we have the clock. This is clock number 1, clock number 2, 3, 4, 5, 6, okay? We are showing only 6 clock cycles here. And X, my X is going to be a 1 at the beginning, and my Y initially is 0. So initially the sequence is not detected, okay? Then at the second clock cycle, my X is also 1. So did I detect the sequence? No, haven't detected the sequence. My previous sequence was 1, 1. It's not 1, 0, 1, okay? Then I have a 0 here, okay? So still it's a 0. So my previous sequence was 1, 0, okay? And then I have a 1. So once I get this 1, my sequence here is detected, okay? It's 1, 0, 1, all right? 1, 0, 1. So my Y will be 1 for this this time, and then it will be after 1 clock cycle. Okay, this is going to be a 0. Okay, this is going to be a 0 for the X. Okay, and at this point here, no, the sequence is not detected. Okay, and then if you get a 1 here, the sequence is detected again, and so on and so forth. Okay. So this is how this is a description of the problem. Any question about the problem? It's important to understand the problem before we proceed to the solution.
Doctor,
Yes.
so it detects only 101, not 0, 1, 0.
Yeah, this is the problem. You can see here. It's 101 detector. Okay, sequence detector. It's 101. But this one here, 010, is not the sequence. It's not the sequence. Okay, so 010 is not my sequence, but 101 is my sequence. Okay, so I assert my output high here. Okay, do you get that?
Yes.
Okay, now I want you to pay full attention here. If you haven't paid attention so far, please pay it now. This is important and very important. This class of problems, sequence detection problems, can be solved using state diagrams, of course. There is a pattern, okay, in which the state diagram is developing, okay? So at the beginning, we say that we have an initial state in which no bits have been received yet, or we haven't detected the sequence. So I'm going to denote the initial state by S sub I. Okay, it's initial. And this is my initial state. So I'm going to derive a Mealy state machine for this problem. Okay, so this is my S sub I, all right? And suppose that I am in the initial state and I receive a 0. If I receive a 0, what happens? I should stay in the initial state. I shouldn't advance my search. Let's say that I receive a 1 on the other hand. If I receive a 1, then I should move to a next state that advance my search. Because I got one bit of my sequence. My sequence is 101. So it starts with a 1. So this is part of my sequence. 1 is part of my sequence. But I still haven't received the sequence completely. So my output is 0 still. Okay? So if I receive a 1, I'm going to advance my search to another state called S1, which means, okay, I'm encoding my states like this, which means I received a 1 so far. Okay? However, if I receive a 0 at Si, then I'm going to stay at Si. 0, and the output is 0. Okay? And this is my initial state, so I should annotate that. It's called reset. All right? Is this clear, guys? I'm going to slow down here because you need to digest this, okay? So why did I stay in Si when I receive a 0 here? Because my sequence starts with a 1, not with a 0. Okay, so if I receive a 0 at the initial state, then this is definitely not my sequence. So I shouldn't advance my search. I shouldn't be looking for the next bit. I should stay at the initial state. Do you get that?
Yes, clear.
Yes.
Clear. Okay. What about the 1? The 1, I got it here, and I advanced my search because it's part of my sequence. It's the first bit of my sequence. So I advanced to this state. So this state means I received a 1. Okay. Now, in this state, I can receive a 0. And this 0 means after this one, it means I'm advancing my search further, right? It's my sequence. Remember, my sequence is 1, 0, right? 1 followed
Yes.
by 0 followed by 1, right? So if I receive a 0 here, then still it's my sequence haven't been detected yet, but I advance my search to another state that is called S10. I received a 10, okay, which is one step away from my sequence, okay, one step away from my sequence. And at this, now this is when I receive a 0. Okay, what about when I receive a 1 at this state? Where do I go?
You go back.
Go back to
Si.
Si. Okay, let's analyze this. So if I receive a 1, I go back to Si. So let's say that I get a 1 here. Okay, so initially I'm in Si, right? I get a 1, so I go to S1, right? And then I get a 1 here. Okay, so I go to Si, as Faisal said. Okay, all right.
I'm sorry, doctor. I think no. You stay in S1.
Let's see why this is wrong. First of all, let's see why this is wrong. It's important that you guys are following, okay? If
Okay.
I receive a 0 here, what happens? I stay in Si, right? As per this loop here, okay? And if I receive a 1 here, then I go to S1, not Si, okay? But notice that my output is 0, even though the sequence has showed up. Do you see that? So this is wrong. It's wrong to go back to Si when you receive a 1 there. Okay? We must stay in S1 because you already, if you receive a 1, then your state didn't change. It's still, you have received the first bit of your sequence, okay? The first bit of your sequence. So if I receive a 1, then nothing changed, okay? Nothing changed. I'm still looking for the next 0, okay? All right. Now, I am in S10, okay? And I receive a 0. I receive a 0. What happens? So you see here, I'm in this. S0 means that I have received 1 0. Okay, and if I receive a 0, then there is no chance. There is no chance that I can reuse this sequence towards my sequence. So I have ruined all the steps in my search. Okay, so I have to go back to the initial state in this case. You see that? I just the battery of my pen, I think it died. Yeah, it's 0%. So do you see why I should go back to S initial when I am in S10 and I receive a 0? Do you see why? It's important to understand why. It's important to understand why. The reason for this is that, yes, can you tell me the reason, Muhammad?
دكتور ماني فاهم بالضبط. المفروض ان نرجع لس 1 عشان
طيب S1, what does it mean?
اس 1
The current bit is 1.
Not the current bit. It means we have received the 1 of the sequence. The current bit is upcoming. It's not yet. Okay, this is the state. Okay, this is the state. This is actually the previous bit, not the previous input, not the current input. Okay, so S1 means that we have received the 1. Okay, we have received the 1, and what? Now let me use annotation in order to until the pin charges a little bit. So S1 means that we have received the 1 and we are expecting the next bit. So S1 means that we have consumed the first bit of our sequence. Okay, now if I am here and I receive a 0 like this, okay, I receive a 0 like this, then what does it mean? Does it mean that I received the 1? Does it mean that these 3 bits are part of my sequence? Answer is no, of course. If you are in S1, you should expect a 1 as your last bit. Okay? You get that, yeah, Muhammad? It's okay to say no. I'm perfectly fine with that. Okay? So what happens is that you are in S10. Okay? You are in S10. Let's prove to you that it is wrong to go to S1 when you are in S10. Okay, so let's say that you are in S10 and you have a 0. Okay, and you go back to S1. Okay, so let's say that you get a 0 after that. Okay, and then a 1 after that. What happens? I need the pen, guys. It's very important to have the pen. I'm really sorry about this. It's unaccounted for situation. So yeah, let me just clear all the drawings, and hopefully the pin have charged enough now. Yeah, okay. So now let me ask you this, Muhammad. Muhammad, pay attention, please. Now we are in here. Let's finish the easy case. Okay, the easy case. We are in here now, and we receive a 1. We receive a 1. Okay. If we receive a 1, it means we received our sequence.
صحيح.
Yeah. So we receive our sequence and we go to the initial state looking for the sequence again, right? Do you have an objection about this? So if we receive a 1, the output is going to be 1, and we move back to the initial state to look for the sequence again. Actually, no, this is not the case. we should go back to S1 again. Because why? Because 101 means that we received the 1 at the end, right? So we have to utilize this one. Why? Because we are saying with allowing overlaps, okay? With allowing overlaps. So we are in S101 here, okay? And we receive a 1, okay, 10, and we receive a 1. So if we receive a 1, then the output is going to be a 1, and we go back to S1. Because here, if we are in 101, then also we expect a 01 to show up, for example, in order to detect the sequence again, like what we did in the example here. If you see 101, then we have a 1 here, and then 101, and then we have a 1 here. We used this one twice. You see, we used it for this sequence and for this sequence. So this one here, once you consume it for the output, okay, you should use it as an input, okay, for the next state. So once we get a 1 here, we should go back to S1, okay, meaning that, and the output is going to be 1, meaning that we received the 1 and we are ready for the next bit of the sequence. Okay, is that clear, ya Muhammad?
Yes.
So now the question is, what if I say, okay, I say to you that if we receive a 0, we go back to S1. You're saying, this is what you're saying, right?
Yes.
So if we receive a 0, we have we are currently in S10, all right? And we receive a 0. Where do we go? You say we go to S1. Okay, this is wrong, by the way, but we are going to show you why this is wrong. Okay, so the sequence now so far is 100. Okay, now if I receive another 0, where do I go as per the state diagram? I am in
You go to S10.
Excellent. S10. All right. Now, as per the state diagram, if I receive a 1, what happens?
You go back to S1.
No. Okay, this is fine. But what's the output?
The output 001?
Yeah, no, the sequence is 001, but the output is going to be a 1, which is wrong. We are saying that we are detecting we are detecting our sequence, but actually we are detecting 001, not 101, as per the problem description. Do you see that?
Yes, it's clear.
Okay, so the correct thing to do here is when you receive a 0, you go to S initial. Okay, and the output is 0. Okay, so now if you receive a 0 and you go to S initial, what happens? And let's just simulate that again. Okay, so we have to also raise this. So if you receive a 0, you go to SI, right? Let's say that in SI you get a 1. Okay, and if you get a 1 here, you go to S1. And if you get a 0 here, you go to S10. All right, and if you get a 1 here, then you go to S1, and the output here is going to be a 1, right? Because we actually detected 101. So nothing is wrong here. Okay, is this fine?
Yes.
Okay, cool. Now the next step. So this is my what we call symbolic state table. Why is it symbolic? Because the states are not like here, for example, in the analysis, we are giving the states binary numbers. You see that? Binary numbers. But here the states are given names. See that? SI, S1, S10. So how many bits do you think we need in every state in order to be able to encode them correctly? The minimum number of bits. This is the state assignment step. Okay, we have to assign our states binary values in order to go ahead and proceed with the implementation of the design. Okay, this is the design, and then we have to implement the design now. So I have SI. I have three. Basically, I need to count 0, 1, 2, right? So in binary, counting up to 2. How many bits do you need? Maximum number of bits.
Counting to 2, you need 2 bits.
2 bits. Excellent. So 2 bits means that you have how many codes? How many codes? 0, 0, 0, 1, 1, 0, 1, 1, right? These are the possible codes, right? And we have how many states? SI, S1, and S10. We need to assign each one of these 3 states to one of these 4 codes. So my question to you, how many possible ways do I have? How many possible assignments do I have? So for example, one possible assignment could be, for example, assign SI to 0, 0, and S1 to 0, 1, and S10 to 1, 0. Okay? Or assign it to this one. Or assign this to this, and this to this. Right? So there are how many combinations are possible now? Think of counting, right? You have buckets, and this is SI, S1, S10, right? So how many possibilities for SI initially? It's 4, right? For SI, I can choose any one of these 4 codes, right? Then once I fix SI to one of the codes, I have 3 possibilities for S1. And then once I fix S1, I have only 2 possibilities for remaining possibilities for S10. So by fundamental theory of counting, you just multiply them these numbers to get the number of possibilities. So we have 24 possible code assignments or state assignments. All right, you can choose any one of them to implement your circuit. Okay, and notice that some of them will result in simpler hardware than others, but we cannot tell ahead of time. So for this reason, we will choose the first 3 codes, okay, for the first 3 codes for the states. So I'm going to assign them this way. This is SI, and this is S1, and this is S10. Okay. So now from this, I'm going to move this to the next page. We're almost done, by the way. I have to and then paste it here and make it smaller to make some room. Okay. All right. Now I'm going to derive the next step, which is, now I've done the state assignment. What is the next step? The next step is derive the 2D state table. Okay. I have the present state. Let's call it A and B, for example. All right. And then the next state. All right, for my input is called X. Okay, so X is equal to 0 here, and X is equal to 1 here, and my output, let me just pull this a little bit to the left. My output, when X equals 0 and when X equals 1. And I want to read now the state diagram and then populate this table. Okay, So my next state is going to be A. Let's call it A plus, for example, or DA, whatever you want. A plus and B plus. And here we have another pair of them, A plus and B plus. Okay? And for the output, let's call the output Y. Okay? We have already called it Y. And how many rows do we need? 4 rows. Okay? 4 rows. Because you have 2 bits for the state, you have 4 rows. We have the state 0, 0, which is SI here. Let me just annotate that. This is my SI. And state 0, 1, which is my S1. Okay, and then 1, 0, which is my S1, 0. All right, and then state 1, 1, which is not used. Okay, it's not used in our case. We could use it for our what we call advantage. Okay, so now I'm in 0, 0. Note, just follow the state diagram. Okay, I'm in 0, 0. I'm currently in 0, 0, state 0, 0, which is SI, and I receive a 0. I receive a 0, so I go back to state SI, and my output is 0, right? My output is 0, and I go back to 0, 0. You see that? All right. What about I am in state 0, 0, and I receive a 1 for X. I go to state what? 0, 1, right? Are you following, guys?
Yes, yes. 0.
And the output is still 0. Okay, Muhammad, tell me the next line, please. You said yes just a moment ago. So we are in state 1, or 0, 1, state 1, and we receive a 0. What is the next state? The state, and we receive a 0. We go to S1, 0, which is 1, 0, right?
0, yes. Doctor, so the X is the receiving value for the variable S1, S1, 0.
What about it?
The X here.
Yeah, it's a serial input. It's a serial input here. Receive it, input.
Oh, okay.
1 bit serial input, okay? Every clock cycle we receive a value, okay? And we only output 1 when we detect 101, okay? Okay, so and for when X is 1, we go to S1, which is the same, 0, 1, okay? And the output will be 0 in both cases. All right, and then what's next? 1, 0. Yeah, and we receive a 0, so we go back to 0, 0. And if we receive a 1, we go back to 0, 1.
To S1. Yes, yes.
Yeah, and here the output is 0, and here the output is 1. This is the only case where the output is 1. Okay, here we don't care. Actually, for why you may maybe part of the requirement is that you choose them to be zeros here. But if you are sure that this sequence will never occur, then it's even fine to put them X's as well. So now,
Doctor,
the next, yes.
why we receive 1, the output?
Why do you receive a 1?
Yes.
When the I couldn't understand your question. So can you say it, please?
And the output.
This one, you mean this one here? Okay, you're talking about this one here. Okay.
Yes, yes.
So here we are in S1, 0. Okay, and we receive a 1. We run S1, 0, and we receive a 1. So the output is 1 here. See that? We detected the sequence
Okay.
already.
Okay. Yes. Yes.
Okay. So in the next class, inshallah, we will continue from here by deriving the K-map, and then we will show you the implementation of the circuit. Okay. All right. Let me stop recording.